Hello. I think you have to trust me because I'm classical. And of course, that could be the first sentence a quantum device may say to you. Right? I'm classical, you have to trust me. Yeah. So I'm Yaoyun, I'm from University of Michigan. So I'm going to assume there's at least one evolutionary biologist here. Remotely, online, watching it. So I'm going to assume no prior knowledge, and you may, to avoid making you bored, I throw in some pictures that you like. So quantum power is incredible. So it's incredible, doing many things. Spooky actions at a distance, if you remember the movie. Simulating quantum physics. Super fast factoring. Unbreakable code, nobody can break it. There are more, but because Jaja was saying more, I couldn't understand what he says. I think it's blah, 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 blah. So the story began with this cat. This is a cat in a thought experiment of Schrödinger. So Schrödinger's cat. It was a very miserable cat. It was put in this metal box where there is a chemical, and the chemical is radioactive. So after some time, this cat and the chemical, they become in a so-called entangled state. And if the chemical decay, the cat will eat that yummy poison and become dead. And if it does not decay, then the cat would be craving for that poison, but not eating it, so therefore alive. Do you actually believe in half-dead, half-alive cats? How many of you believe in? Not many. And that's what my student Smita felt when she took my introductory quantum computing course in 2002. So I went to Michigan as an assistant professor at the time. So she was talented, many things, and one of her talent is write poems. So here is the poem she wrote. It's one of the 4 poems. All the poems are in my website. Okay. So I'm going to read it to you. A group of physicists performed a hoax about a cat half alive, half dead in a box. The equations so well worked out and observations to doubt. Only mathematicians fall for such jokes. So indeed, quantum power is incredible in a negative way. Hard to believe. So there are reasons that we don't trust the quantum devices. First of all, we are classical beings. We can't just touch the cat and say, yeah, this is Schrödinger's cat. You can't do that. And there are technological challenges. It's really hard to make quantum computers. So I Googled the record of factoring using quantum computer. I think the current record is the number 143 last year. And even experiments that are supposed to verify they are indeed quantum entanglement are not conclusive. You missed the best joke. So there are loopholes for entanglement experiments. And there are security concerns. This chip, alleged quantum chip, might be certified by a 3-letter agency. And whether or not you trust it depends on the situation. Sometimes you may not want to trust it.
It's 11 times 13.
You are faster than that quantum computer. So the question now becomes, now we don't want to trust the quantum device. Can we still reap the benefit of the quantum power? That's the main question that I'll try to answer. And the answer is, yes, we can. We don't trust this guy. But we still have to work with it, and we can make it work. So I'm going to start with the general principles and approach, the general paradigm of making untrusted quantum device work. And after that, I will talk about 3 applications: untrusted device quantum computation, untrusted device randomness extraction, and then untrusted device key distribution. I probably will spend most time on the second topic. Now I'm going to start to describe the general framework or general approach of making untrusted quantum device work. The foundation is what I called classical test of a quantum duck. So if this works like a quantum duck, quack like a quantum duck, and behave like a quantum duck, then it will be a quantum duck. So the classical test will be interactions between the user, us, we are classical being, with the untrusted quantum device. And we will check if it behaves like a quantum duck. And the test we will perform, they will have the property that if the device is behaving exactly like an ideal quantum duck, then it must be the ideal device. And furthermore, this notion of robust self-testing, this is the noisy version of the previous self-testing. If the device is behaving close to the optimal quantum strategy, then the inner working of the device must be close to the ideal quantum device, both in the quantum state and also in the measurement, up to some local isometry. Okay, so that's the first part, the first of the 2 most important ingredients in the general framework, self-testing. So suppose we have some game to do the self-test. How can we make use of it? The strategy is to mix work and play. If you have children, how do you make your children do the housework at the same time enjoying it? That's a challenge. If you can accomplish that, that's a great accomplishment. And that's precisely those results I'm going to survey accomplish. Mixed work and play. The consequence is that the device cannot tell if it is work or play. It cannot tell if it is work or test. And if it tries to avoid work, it will risk failing the test. So the protocol will have the following 2 guarantees. The first one is called completeness guarantee. It says that if the device is honest, therefore the job is well done, then we should pass the device with overwhelming probability. Then the second property is soundness property. It says that on any device, good or bad, our protocol almost always reject or accept a very well done job. So combined with the completeness, it implies that, all right, so if the device is honest, then we will pass it with, it implies that the chance of us being fooled by a malicious device is very small. Okay, so I have finished describing these two important ingredients in making untrusted device work. One is self-testing. The other is to come up with a strategy of mixing work and play. And so now let's look into more details. How can we make this strategy work? So come back to self-testing. So how could self-testing be possible? Okay. So it's impossible if there's no additional constraints on a device. If the device can do whatever he wants, then there's no way we can accomplish our goal, because it will just tell you whatever you like to hear. Some of you may know this story. So therefore, we need to impose additional constraints on the device. Okay. And here's one particular way of enforcing additional constraint: spatial separation. So we can require that the device has multiple parts, and we place those different parts far away from each other, so that because of spatial relativity, these two parts or multiple parts, they cannot communicate with each other within the short period of time that we will run part of our protocol. So this is a constraint that classical beings like us can enforce. Okay, so now I'm going to give you 3 examples of self-testing. The first one is the so-called CHSH game, named after the authors of the idea. So the game works like this. We have a device that's 2 parts, A and B. So when a game starts, each part receives one single bit. So this part A receives X, and part B receives Y. And each part is required to output 1 bit. So A outputs this little a, and part B outputs little b. And throughout this process, because Einstein is in between, there's no communication between these 2 parts of a device. So the rule of the game is the following. When the input x and y are uniformly random, and so the device will win if their output bit, the XOR of the output bits is the same as the AND of the 2 input bits. In other words, when one of x and y is 0, then A and B must be the same to win a game. And if x and y are both 1, A and B must be different to win a game. So here's a very obvious classical strategy. Out of the 4 combinations, 3 has a 0 in its input. So therefore, if both A and B output 0 all the time, they will win 3 out of 4 cases. It turns out that the best classical winning strategy is no more than 3/4, and that can be achieved. So this bound saying that the best classical winning probability is upper bounded by some number. This is called a Bell-type inequality. And as we have just described, there's a strategy to accomplish, to reach this 3/4 chance. So for quantum devices, they could play the game in a broader way. They could start sharing entanglement before the game starts. And then, once the game starts, each of the 2 parts applies a local measurement determined by its input. And there's Teresen proved that the best quantum winning probability is no more than this number, and cosine square of half a. So that's 0.85, and this can be achieved by a protocol we also call it CHSH protocol. CHSH game is a strong self-test. So in the 90s, people already knew that any strategy winning with that optimal quantum strategy must be the optimal quantum strategy. And more recently, we knew that it's a robust self-test, and furthermore, is the strongest possible robust self-test in general. And if the winning probability is epsilon close to optimal, then both the state and the measurements are square root epsilon close to optimal. And that's the strongest possible. Yes, Mario?
Why do you call it self-test? I am puzzled by that expression. So who is self? The Einstein is self, or the A and B are the self?
I think it's just historical reason we call it self-test. I wasn't the first one to describe this, but I think the meaning there's a reason for calling it so. The validity of the devices can be demonstrated by its own behavior, instead of we take away the hook and look inside. Okay, I think Umesh and Ben Richard and Unger, they call it rigidity of the game. That's also an excellent name as well. So there are many other robust self-tests. For example, there's a famous GHZ game. And one reason that this is very interesting and important is the optimal quantum strategy actually always wins, while the optimal classical strategy is still below 1 probability. There's this class of binary XOR games where the input and output are binary bits, and whether or not the device, when it wins the game, depends on the XOR of their output bits. Of course, it depends on the input, but then it also depends on the XOR of the output bits instead of individual output bit. Okay. So those are called binary XOR games. GHZ, CHSH, both are examples of binary XOR games. So Carl and I characterized the class of strong self-test binary XOR games. There is a very simple criterion for deciding if a game is a strong self-test. So that's my first example. One-shot test of self-test of one-shot CHSH game. So how about we play the game multiple times? We play the game sequentially. And what can we infer from the average winning probability? If the average winning probability is close to optimal, what can we say about the untrusted device? So Richard, Unger, and Vazirani proved that if, on average, this sequence of game wins very close to optimal, then there's a big chunk. So for a random chunk of sequential games of substantial length, then is close to the tensor product strategy, the principle of the ideal strategy. So this is the consequence is very strong because it says that for this chunk of gameplays, the strategy is very close to tensor product form, and therefore you can substitute the property of using a tensor product strategy in situations that when we have guarantee that this would happen. Yes?
Is this a parallel repetition or a sequential repetition? Or
What would you say?
Well, this was proof for sequential.
Sequential. Yeah.
Sequential.
Does it need to be?
Well, the way we did it, yes.
Although the fact that you separate, the fact that there is no in between games communication without differentiated from the usual notion of sequential.
So for polar repetition, it's not a priori clear that you cannot get better than the product. So if here is clear that you cannot get better, is it clear? Or then it should be a sequential repetition.
So this is my second example of self-testing. My third example is self-testing graph states. So graph states are quantum states that corresponds to graphs. Suppose you have a graph like here. Then the graph state, in the graph state for this graph, each vertex corresponds to a qubit, and each edge corresponds to some interaction or some operation we will apply to those two qubits. So graph states can be highly entangled, very complicated states. And so McKay proved that graph states are robust self-testing, and in a recent paper he proved that if a graph state, so if a multiple part device is passing the test with high probability, then the corresponding error in the strategy is upper bounded by a function linear in the number of vertices. So in his previous work, the number of vertices appears as exponential function. He improved that to linear, and that's important. Yes.
What's the test? Is it complicated?
The test is it's two parts. No, it's not complicated. It's basically testing if it satisfies the stabilizer relation.
Okay.
Yeah.
Sorry, what is the graph state? What is the graph state?
You can think, so there are two ways, at least two ways to describe it. One way is this. So I would start with a state where each qubit is zero state. Okay. I apply Hadamard on each qubit. Then for each edge, I apply a control phase flip, meaning that if they're both 1, I change the sign by -1. Okay. Another way to so this is a very explicit way of constructing it. Another way to think about it, it's a state that is stabilized by a group of Pauli operators, where this group is this: you have sigma x on each vertex and sigma z on its neighbor. So for any of those, it will stabilize this state.
Can you write it down like sum of something?
Sure. It's sum of if the vertex is v. So this is a 0, 1 string indicating which vertex is chosen. And then the sign is either plus or -1, depending on if the subgraph induced by V prime has an even or odd number of edges. Okay. And I didn't normalize the state. Yes?
So what you're testing in the CHSH, is both the state and the measurement.
Right.
And here, it sounds like the measurement is you're taking that for granted. And
No, it's also testing the measurement. It also, yeah. It would send.
The measurement's a bunch of single qubit measurements?
Right.
Okay.
They're Pauli measurements.
Over half an hour.
Okay. I think I'm going to skip how you can do untrusted quantum computation based on those self-test results, because I have additional materials I want to focus on. So maybe I should mention the untrusted device quantum computation. There are two main results that I had planned to tell you. One is based on sequential CHSH test, and the other is based on graph state. Actually, I regret what I just said because I think they are very important results. So, and I'll just go back to where I left. Okay, now how can we do untrusted device quantum computation based on those self-testing results? I want to first set up the background. And so the first step is to separate the quantumness, the essential quantum part from quantum computation. Kind of extract the essential quantum part. And before I talk about that, I want to give you an analogy. Say randomized algorithm. So one can think about randomized algorithm as at every step you toss a coin and decide what to do next. Okay. An alternative view is that randomized algorithm is nothing but a deterministic algorithm that has an additional input being random bits. Okay. So likewise in quantum computation, there are ways to separate the quantumness or quantum resource from the computation. We can equivalently express quantum algorithm as some very restricted quantum operations, like single qubit measurement, that are applied to some special quantum resource, which does not depend on the input. So here's one way of implementing this separation of the essential quantumness and restricted operations. And this is computation by teleportation by Gottesman and Chang. The quantum resource is a bunch of EPR pairs, very special 2-qubit quantum states. And the restricted quantum operations, they are Bell measurements plus single qubit operations. Now here is a high-level description of the Richard Unger and Vazirani untrusted device quantum computation algorithm. So the untrusted device has two parts, A and B, and an ideal implementation would have a lot of EPRs in there. So the protocol will mix, so the user is a randomized classical verifier, and he will interact with both A and B, part A and part B. And the strategy is to mix the sequential CHSH test, which work for teleportation-based computation. So if the A part and B part are not following instructions, they will risk failing the test. And all means implementation would just just carry out the instruction and should be passed with high probability. So moving on to the quantum computation, untrusted device quantum computation using graph state. So the corresponding separation of quantumness from quantum computation is the so-called one-way quantum computer, where you start with a graph state, and then you do single qubit adaptive measurement on a graph state. So I have explained graph state what a graph state is. So now the quantum device has many parts. In fact, each vertex is a device component. And so therefore, each component for a vertex would not communicate with other vertex component in a protocol. So the protocol consists of a single message to each component and a single message back from each component. And again, so the strategy is to mix test with work, and so on these devices will store the gigantic graph state and just apply the instructed measurement. So the difference with the Richard Unger Vazirani protocol is that here it's one run parallelly, one bit, one message forward, one message back. But in previous protocol, it's interactive, and only two parts of the device. Yes, Anne.
Oh, I don't know if you mentioned multiplier difference. The difference here is the number of provers.
Right. The number of provers here is multiple. The number of components is basically the size of the circuit being simulated. But in the other paper, it's simply two parts. Yeah, that's a very important difference. It's kind of trade-off between the number of provers and the number of runs. Okay, so let's finish my first example of application of untrusted quantum device. I'm moving on to the second group of applications about generating random numbers using untrusted quantum device. So randomness is very important, is vital for our modern day information processing. So it's vital for digital security, for randomized algorithms, and for scientific simulations such as weather prediction, weather forecast, and for gambling, and many other things. So this is what we hope for randomness. We hope that we can get very high quality randomness and close to uniform. So it's quantified by how close it is to uniform. Sorry about that. And also how secure it is. It's also an important aspect of high quality. And we also want to have a large quantity of it. And actually, I did estimate. I talked to my computer security guy where random numbers are used in the current technology. So of course, they are used in the public keys, right? But those are only tiny portion of the total number of random bits we use, because every time you have a encrypted web session, you would have used random bits. And in fact, every packet would have the packet number is also supposed to be a random number. And I did a calculation, maybe 1 trillion, if 1 trillion bits a day in the whole world is too much, it probably would not be 1 or 2 magnitude away. So we need a lot of random bits. We also hope to minimize the assumptions we make about the random number generator. And we don't want to trust if we don't have to. So currently, this is one example how we get random numbers. So Linux is run in a lot of devices, including your mobile phone if it runs Android. So Linux random number generator is this. So it's a deterministic process. It will collect inputs from the system boot time, from the current process ID, and from user input, and from hardware like Intel's on-chip instruction. There is an instruction called RD-RAND that is based on some thermal noise, according to Intel. So you collect all those inputs and somehow mix them together, and then to get initial randomness. And whenever your application needs a random number, it would deterministically produce one. So therefore, after collecting the input, you will apply some pseudo-random number generation, stretching the key to a longer key, the string to a longer string. So how does it do in our world? There have been numerous many reports of things go wrong. And the lack of initial randomness has led to a large number of broken keys. So I have a colleague, Alex Holloman, so he and his collaborators, they downloaded a lot of keys from internet, and they broke about 1% of the RSA or DSA keys, because a lot of those keys, they share factors. It's very hard to factor a number, but if you have two numbers sharing a factor, it's very easy to find them, right? So, and they explained that there are only a small number of device makers for those devices, and it turns out that a lot of them just get the same initial randomness. And there are news reports that there are backdoors built in chips, and also even in standard. Okay. And also the security of current random number generators, they are based on unproved computational assumptions, so therefore vulnerable to progresses in algorithms and in technology. Okay, so here's the question. So you have a random number generator. How can we be sure the output is random? Okay. It's not just a very practical question. It's also a physical question and maybe philosophical question. So how can we, how could fundamentally unpredictable events are possible in our world? Okay, so a random number generator is creating some events, right? So in our physical world, how could this kind of unpredictable event possible at all? So where do we get the initial almost perfect randomness? The answer is that we can't be sure, we can never be sure. So anybody knows where this picture comes from?
Matrix?
The matrix, right? So what if we are all subjects of some experiment and everything, and the fact I'm talking here is determined, maybe it's the Big Bang moment, maybe Patrick could have a better story. So we can't really be sure without believing in something. First of all, we have to believe that randomness exists. Okay. I may sound like a matrix character saying, maybe Moses saying. Right? So we can't be sure. We can't be sure the output of a randomness extractor is random without accepting assumptions. So now the key question becomes the following question. So how can we generate a large number of provably unconditional secure random bits with minimal assumptions? So that's the central question we're going to study. So let's look at how classical theory deals with this problem. And I want to claim that classical theory is inadequate because of the following requirement. It requires having two or more independent sources. So the classical theory of randomness extraction, it models weak randomness as mean entropy string. So imagine this chimpanzee is providing you some randomness, and mean entropy means that if the mean entropy is k, that means that the adversary cannot predict with more than 2 to the minus k probability. So the theory has a theorem that says that randomness extraction, meaning that getting almost uniform output, is possible only when you have two or more independent sources. So one may coming from this chimpanzee, the other may coming from Simpson, and they must be independent. Okay. How can we be sure that two sources are independent? That's just impossible. There's some argument to argue that it's just impossible for deterministic algorithm to tell if two sources are independent or not. Okay, so if we have to rely on classical theory, we have to make sure that two sources are independent, but it's impossible to do. So here's the big question: can we get around? Can we get around this independence requirement? The answer is yes. If we trust quantum devices, then it solves almost all the problems. In fact, there are commercial products. And the reason is that the postulates of quantum mechanics have randomness built in. It promises true randomness. For example, if we prepare the state in this plus state, 0 plus 1, and we measure using the so-called computation basis, then we get output 0 or 1 with equal probability. And this is probably one of the most simple state to prepare, so therefore you can get a lot of randomness cheaply. And there are commercial products available. This is a product, I take this from the website of ID Quantic. So they have multiple lines of product claiming generating randomness is true quantum randomness. And what is cut off here is passes ALL, or randomness test. I'm not sure what a quantifier quantifies, but all of the tests that they have done. Yeah. And it claims to be high rate and cheap, meaning that it's quite easy, and whatever other property. And down there it says that this product has been officially certified by the Swiss government organization. It's not 3 letters, it's 4 letters organization. But the problem is, okay, should we trust the device? Should we trust the device not being malicious? Should we trust the device working properly? Should we trust the device maker? And should we trust the 4-letter agency certifying that device? So in situations that we don't trust, then we want to come up with methods for getting randomness from untrusted quantum device. So there are two topics, two problems people have studied on how to get randomness from untrusted quantum device. Both were initiated by Kovac with different collaborators. The first problem is called randomness amplification. It was first proposed by Kovac Renner, 2012. So the question is this: suppose we don't have perfect randomness at our disposal, and what we have is an SV source, sense-out Vazirani source. A sense-out Vazirani source is a bit string where every bit is of some amount of bias and some amount of randomness conditioned on all the previous bits. So it's not perfectly random, but it's probably the closest to perfectly random. Sorry. So we have SV source. That's the only random source we have, and we have untrusted devices. So can we make use of those SV source string and interact with untrusted devices and output one bit that is near perfect random bits? So that's the question they study, and they call it randomness amplification. And they have some physical motivation for that purpose. The other problem is called randomness expansion. It appeared in Kovac's thesis in 2006, and also in a journal paper with his then advisor Kent in 2011. So now we have perfect randomness, but we want to get more after making use of some untrusted quantum device. It is two questions people have studied in the past. So my collaborators, Kaimin Chang and Xiaoli Wu, who is sitting here, we have this framework for extracting untrusted quantum device, extracting randomness out of untrusted quantum device. So I'm going to describe this framework. So this is part of this is going to be in QRP, coming QRP. So in this framework, there are a few. So here are the players and components in our framework. There's an adversary who is all powerful, but we are going to assume quantum mechanics. And the adversary prepares the device and may entangle with the device. And then you will give the device to the user. Okay. So after the adversary hands over the device, it cannot talk, it cannot communicate with the device, and it cannot change the device after our protocol starts. But so it may be set up to be correlated with adversary herself. The device has multiple components, and the user is a deterministic classical being. It can restrict the communication among different device components. So we have an adversary and a device and user, and there's a fourth thing. There's a mean entropy source. This is a classical randomness source. And we really need to have some randomness that the adversary cannot totally predict. Because if there's no additional randomness, because the user is deterministic, and so the adversary can manipulate the user in any way that he wants. So we need to have additional randomness that the adversary cannot predict. Therefore, in our framework, this deterministic user is going to take in this mean entropy source, interact with multiple components, with different components of the device, and at the end, you will output an random string, and together with a decision to accept or reject the protocol. So we can see the previous two problems, amplification and expansion, in this framework. So for amplification, recall that for the randomness amplification problem, we start with an SV source, going through an untrusted device and outputting a bit. Okay, so this is a special case of our framework where we are doing randomness extraction that has no seed. So in this iteration of randomness extraction, seed is always as in most authors would interpret seed as perfectly random string. So therefore, this case corresponds to seedless extraction, where the extractor has an SV source to assist its work of extracting randomness from the quantum device. Okay? So there's no perfect randomness available. And that's why we call it seedless extraction. And so seedless extraction is impossible for classical extractors. Unless you have additional independent source. So seedless extraction using only one source is impossible. That's basically deterministic extraction. So we know deterministic extraction is not possible. And the first example is the SV source example. So seedless extraction with single source is deterministic extraction, which is impossible classically. But in the quantum setting, it is possible. It's a big contrast. So the second problem of randomness expansion, so recall that here we start with perfect randomness. We want to get more out of interacting with untrusted quantum device. In our framework, it is precisely a seeded extraction. So this classical source is a perfect random string, and it's the seed to assist the extractor to get random outputs. So I want to emphasize a different view of this framework and the previous two problems. So in the previous problems, people think about the randomness that we get at the end came from is classical source. But here we think more appropriately, we should consider the randomness being inside the untrusted quantum device. And the role of the classical Binet entropy input is to assist the protocol in unlocking those hidden randomness in the quantum device. So with this framework, let me describe a list of ideal properties we want to have for this kind of extraction. Yes?
So during the extraction, are you communicating back and forth with the device?
Yes.
Or?
Yes. Yeah, there will be back and forth interactions. Yes.
So it's not just that you get some kind of string from the device and then you are turning it into a random string, but rather you are kind of testing the device.
Right. We're going to test the device. Yeah. I'm going to give you a little bit more details. Okay. So what are the nice properties we wish to have for extracting randomness out of untrusted quantum device? The first one is security. Ideally, we want to have the strongest possible security, which is quantum security, security against quantum adversary. Second is quality. We want to have negligible errors, negligible completeness error, and negligible soundness error. And I should point out that soundness error is limited by the mean entropy source, because once the adversary can guess correctly what that mean entropy source is, there's no security at all. Okay, so there's a limit for soundness error, and we want to approach that limit. So recall that soundness error refers to when the device is malicious. Then what's the chance of us being fooled, of accepting something that's really bad? Okay, and there's a limit determined by the mean entropy, classical source, and ideally we want to reach that. Thank you. The third item in our wish list is the output length. We want to output a very long random string, and ideally we want to extract all the randomness hidden in that untrusted device. And I have to say that it's not clear to me, and it's one of the open problems, what exactly is the full capacity of randomness that can be extracted from a untrusted device. Or suppose you fix an implementation, you fix an ideal implementation, what exactly is the maximum amount of randomness that can be extracted out? And that's still not quantified. The fourth item in our wish list is for the classical source, we want to be able to work with an arbitrary, a general mean entropy source, instead of restricting the source to be something that have additional structure, like SV source. We want to work with all general mean entropy source. And we hope that everything else being equal, we want to use the minimum, the smallest mean entropy source. So those four things are in my basic list. So I have a separate list that I call premium list. And those items are critical for protocol implementations. Robustness. It should tolerate a constant level device imprecision, both in each basic operations and also in fighting against decoherence. So if we have a protocol that works only when the device is perfect or almost perfect, then in practice, it's going to be very difficult for us to pass the ideal honest implementation. So it's very critical for protocol implementation that the protocol tolerates noise. The next item is efficiency, and there are different aspects of efficiency. We want to minimize the number of devices. They could be expensive, or enforcing no communication between different devices, different parts may be expensive. So we want to minimize device number. And computationally, it also should be efficient. We don't want so it will be very undesirable if the protocol requires a large quantum memory that will store the quantum state for a long time. Okay, and the smaller the requirement is, the better. So those are in my premium list of the wish list for randomness extractors, extracting from untrusted quantum device.
Sorry, I
Yes.
thought you had only one device.
Sure. Okay.
0.6 you say you
Good.
have many
Right.
devices.
Right.
If you have more devices, then classically you can do extractions.
Okay. So if you have more than one devices, so it's possible those devices are correlated. So therefore, it's not. It does not satisfy the classical assumption of independence. So we do have to consider situations that you have multiple devices. And I guess I think I'm using a convention that a device could have multiple components, and then some other authors, they would think about each component as individual devices. So my convention is that if I have multiple devices, when one device is working, there should not be communication between this device and other devices. So I think either way, so thinking about each component as one device is also fine. But my convention is that when I use multiple devices, then when one device is being used, there's no communication between it and the other devices. Okay, thank you. All right, so we have these two problems people have studied, amplification, expansion, and they correspond to seedless extraction and seed extraction. So let me first focus on seeded extraction. So in this area, my experience is that the protocol, after this important paper, Vazirani Vidick, and the protocol is kind of obvious, but the difficulty is in proving it works. So the protocol of those works are more or less the same. So let me just describe this general framework. So in this framework, we have one device, and it has two components. And the protocol consists of playing sequential CHSH games, or maybe some other games. And the protocol will make use of the random bits. Now it's uniform random bits because we are doing seeded extraction. Making use of those bits to choose a subset of those games for testing. Okay, so the device cannot predict which game is chosen for testing. And the other games will just be, generating games, or games that we use to generate randomness. So in a test round, the user will feed the device components random input. But in the generating round, it will use some constant input. Okay. So therefore, in the testing round, it will consume additional randomness. But in the non-testing round, in the randomness generating round, it will not consume additional randomness. And the protocol aborts when the device is losing too many test rounds. Okay. Otherwise, it succeeds. So what's the relation of self-testing and generating random numbers? It turns out that the optimal quantum strategy has the property that the output bit, A, is uniform to all parties. Of course, A is known to the device and device A, the device component A, but other than the device component, A is just random to everybody. Okay. And by strong self-testing property, if the strategy is close to optimal, then this output bit A is close to uniform to all. Okay, so that's the basic building block for those protocols. So let me describe intuition why it works. And then after this, I'm going to jump to, I'm going to fly in quantum speed to one slide, and then I will conclude. So the intuition why this work is this. So here's a diagram for testing round. One of those 4 combinations is chosen to play the game. But in the generating round, only this fixed input is chosen. So you see there's the intersection of these 2 sets of possibilities. Or I mean, this pair 0, 0 also appears with 1/4 chance in the testing round. So if a malicious device is playing smart and trying to cheat when he sees 0, then he risks losing the test. So therefore, trying to cheat will risk losing, failing the test. As a consequence, the winning ratio of the testing rounds, because those testing rounds are chosen randomly, so the winning ratio of those testing rounds is a good estimate of the winning ratio for the generating rounds. And strong self-testing ensures that the output is random intuitively. That's the intuition. That if suppose now the protocol does not abort, that means that in testing rounds, the device is winning very close to optimal. And that by this statement it implies that in the generating round, a large fraction of the generating round are also close to optimal strategy. So that, and then if a strategy is close to optimal, that bit is close to uniform output. So it seems that putting everything together, if many of those generating rounds strategy are close to optimal, then the output should be random. Okay, but the actual proof is very difficult. In fact, I'm not sure if this is actually true. So intuitively, it sounds reasonable, but mathematically carrying out the proof is very challenging. Okay, maybe I'll just mention that this work of Carl sitting here and me, we accomplish similar parameters with Vazirani Vidick. So from k uniform bits, we can output exponential in k output bits, and with exponential in k to some power error. And this is when n is a large number, and so of course we need to have this number of quantum resources to start. So the additional features we accomplish is our protocol is robust, and so that means that each game need only to win with optimal, with some universal constant below the optimal quantum strategy. And we also allow in between rounds communication for the device. So there's a button of the device. After each round, we can press the button, allow them to talk to each other, establishing a fresh copy of EPR pairs, for example. And consequently, we don't require establishing a lot of entanglement. Suppose we now put 1 million bits, so now we don't have to prepare 1 million pair EPR, and we don't have to maintain them in that state for the whole process. And we also allow any game from this class of strong self-test to be used as a building block. And also, this protocol translates directly to QKD, so we can do key distribution with untrusted 2-part device or multiple part device, and at the same time expanding randomness. I'm going to jump to.
Can you explain the last point again?
Sure. And translation. I mean the translation to QAD.
Yeah.
So, all right. So this protocol, you have 2 parts, right? Imagine that in the QKD setting, Alice has this part, and Bob has this part. And they're going to simulate this protocol. Okay? And a lot of discussions will be public. Okay? Now, it turns out that our protocol will still work. So if Alice and Bob simulate this random expansion protocol with some careful adjustment, especially in the classical post-processing part, then what it can accomplish is that they can start with k random bits. In the end, they will share a key of exponential in k number of bits, and using untrusted quantum device, and it's secure with a security parameter of that. Now, I have talked about seed extraction. I didn't have time to talk about the seedless extraction, but I will just talk about the combination of these two works. Hmm? Yes, I will try to finish.
Sorry,
Mhm.
can I continue my question?
Sure.
How is it related to, like, there are other techniques for doing device-independent quantum key distribution.
Mhm.
So this is just another way of achieving the same.
Okay, good question. I think the other known protocol okay, so I know of only one other protocol achieving untrusted device quantum key distribution that is robust, and which is by Vazirani Vidick in 2013. So there, to output n bit key, the initial randomness that Alice and Bob need to share is also linear in n. Okay, and the difference here is that we can start with polylog of n shear randomness. At the end, we get n bits out. But the shear property is that quantum secure and it's robust. And one additional difference is that we also allow any strong self-test in our building block, and because our expansion protocol allows that, and the Vazirani Vidick protocol uses a specific game. Okay. So I'm looking for a slide. Let me see. All right. So the protocol I just described by Miller and me, it does seeded extraction. And the other protocol that I did not have time to explain, this accomplish seedless extraction. So combining them together, what we can accomplish is the following. So imagine that the only randomness we have is a mean entropy source of certain k mean entropy. So through this protocol, we can produce linear in k bits of random string, which is random to the device that will be in this protocol. Okay. So the adversary might know quite a bit about this, but it's okay. The important thing is that this is random. This is random for the devices. So after the MS protocol, we can get n bits out. And this n and k, there's no relation between them. In other words, n can be arbitrarily long. And so start from k mean entropy source, we can get unbounded number of bits out. So the importance of k is in the quality parameter. So how close our n bits are to the uniform n bits, and that is a number that's determined by k. So we almost reached the limit of exponential in k. Okay. And the protocol is robust and is built based on an arbitrary strong self-test. So I should just finish, and I'm going to be here all the time, many days. So I have a lot of open problems. I consider some of the most important problems in our area. So feel free to talk to me. I'll be happy to share with you those problems. Okay, thank you.
Any more questions for Yaoyun?
Yes, Anne. The major results, open problems. Okay, good question. Shouldn't have closed it. I think it's different people may give you different answers. So for me, okay, so I have a list of problems, but here's if you ask me for a single one, here's a conjecture. So earlier, sorry, I have to go back. So this protocol that does CDD's extraction is not very efficient. It makes use of a lot of devices. And running time is not very good. So if you recall that the output, the parameter, the quality parameter is of cryptographic quality, then the time complexity is not efficient either. Okay. So my conjecture is that we can use two component, one device, to do the whole thing, to the computation. Meaning that you could modify million-sheet protocol so that instead of starting with uniform seed, you start with k million-sheet seed, so source. Then you can get almost perfect output randomness. And that's my favorite problem at this point. And of course, other problems include negative results. What's the limit? So I have this wish list for this new framework. And there are a lot of parameters. So what are the? Is there a single optimal extraction protocol where everything is optimized, or maybe they are incomparable extraction protocols? Some optimal in some way, some other optimal in some other way. So finding out a limit would be my other favorite problems. Yes.
I have a question. Are there games, natural games, that don't have good self-tests?
Sure. I think we can construct those games.
What do they look like? Or?
So basically, even if we restrict to binary XOR games, right? So what I know the self-testing property depends on basically it's a property of a polynomial associated with the game, and you can construct a polynomial in such a way so that you can get any behavior of self-testing degree. Carl, would you agree with me?
Yeah. So I guess trivial examples would be games where the maximum classical score is the same as the maximum quantum score. Those are not self-tests. But then there are also ones where the maximum quantum score is higher, but there are actually multiple different strategies that will achieve that score. Okay. And those are not self-tests.
Okay. So I have to add another important problem I feel very important, very fascinating. And it's more abstract. So the randomness extraction is more particular. Right? The abstract problem is to characterize all self-testing games, or all robust self-testing games. And we have found out classes like binary XOR games. There's some subclass of being strongly self-testing. And for graph states, we also have a class of states being self-testing. And what are the most general class of games that are self-testing? And a lot of protocols we work with, I don't feel that a specific game used is important. So the intuition behind how they work is very general. So there must be some very simple property making those things work. And so asking this so characterizing all the self-testing or strong self-testing games, I think would be a step of identifying the essential features, not make all those untrusted device protocols work. And that to me is a very important fundamental question.
Can you do this untrusted randomness expansion? I mean, self-testing appear in all protocols we've seen so far for it?
Definitely, yeah. So the proof card I critically rely on our characterization of what is a strong self-test. Now there's a geometric explanation, but I'll be better in explaining that. Yeah. And it was magical that that property turns out to be critical for our proof. Yeah. Unit is something about a geometric picture of.
Oh, okay. Yeah, I mean, so like, what the self-testing guarantees is that any given strategy, so if your score is within epsilon of being optimal, then there's one particular strategy that the device must be using. It must be using something very close to that one optimal strategy. And what that means in this context is any measurement that the adversary could perform on an external quantum environment will give her very little information about what strategy was used by the device, because whatever was contained in the device is very close to this one optimal, not entangled, not strategy that has no outside entanglement strategy. And so, so that's sort of the basis for making the conclusion that the adversary gets very little information, for making the conclusion that it is quantumly secure.
It kind of feels like an eigenvalue gap kind of thing.
Yeah,
I mean,
it is a little like that. Yeah, and I think that's also kind of where the O of root epsilon error estimate comes from, because it's a lot like the maximum eigenvalue of an operator.
So a consequence of what Carl described is that for those strong self-test games, it turns out that any device would have a honest component, an honest measurement component, just by the property of the game. Yeah, and that's an important step in our proof.
All right, let's thank Yaoyun again.